chapter 13. I'd like to be out of 13 today. It's a very long chapter, and because of the way the semester is sort of set up with the day off that we get, I don't want to be stuck in 13 forever. So today we'll talk about oxidation. I'm going to talk about the opposite of what we did with borohydride and lithium aluminium hydride, and instead of introducing hydrogen, we're taking hydrogen out. And so the molecules will become more oxidized, they'll have more oxygen involved, and this is a fairly complicated process. I'm going to hold off on a mechanism for this one so far because it needs a chapter later on. There's more material to think about this mechanism, so we won't be doing the mechanism for the oxidation here just yet. But we do need to worry about the process. We need to worry about how to use this in synthesis because you'll be seeing synthetic problems a lot. You'll be seeing lots of different types of problems as we've been looking in recitation, lots of different formats for the problems that will be on this first exam and then throughout the term. So this little slide here is the beginning of the end of the chapter. It's the discussion of how to go in one direction or the other. If you're looking at what we did earlier, we did reduction, in which that was introducing hydrogen. So in this case, we brought in, for example, H-, and we got introduced to borohydride, lithium aluminium hydride, and those are very powerful reagents that will do that job. And we often had to quench that, and that's where that proton came in. So that's done. We know how to do that if you have a carbonyl starting material. What we haven't done yet, and we will do today, is remove those hydrogens. Why do you need to do that? Why not just go in one direction? Well, often you can get from nature a molecule that happens to be an alcohol, and you want to turn it into a carbonyl, because carbonyls are very useful because you can bring in all sorts of nucleophiles to attack that carbonyl. That will be the equivalent of the alkyne chemistry from last year. The alkyne chemistry from last year was all about making carbon-carbon bonds with a terminal acetylide, and that was kind of limited. But now we have a much more versatile system in which we have a carbonyl present. So you have to be able to make carbonyls. All right, we'll start off by making aldehydes and ketones, a little bit of carboxylic acid chemistry, and that will become just as useful, if not more useful, than and more flexible than the alkyne chemistry from last term. So we left off talking about the idea that some of these systems, there are limitations. If you start out with a primary alcohol, it's very difficult to stop at the aldehyde. You'll see why. We talked about this a little bit in recitation. The idea that a primary alcohol has two hydrogens on the carbon with the OH group, and both of those can be removed sequentially. So in this first reaction here, we are taking out H from there and H from there, and that results in the electrons being left over to form a carbonyl, to form a pi bond, and you get this aldehyde. Now, aldehydes are very, very useful because you can use them as electrophiles in Grignard chemistry, but they can be a bit tricky to work with and they can be a bit tricky to isolate. So what we'll see today is that a certain set of reagents, you will not stop at the aldehyde will go further and get oxidized to a carboxylic acid. Now, the reason this can happen is you have this extra hydrogen left over, it can come off, and we can replace it with an O, and you get this sequential oxidation up to the carboxylic acid. So what you should be seeing now, if you're making flashcards and keeping track of this stuff, is that we have synthetic methods to go from simple primary alcohols all the way up to carboxylic acids. And we will talk about families, we'll talk about the different relationships between these molecules. I think this is the first time we've really related these two things. Okay, they're very different. Primary alcohols, you know they do some chemistry, you'll see a lot more chemistry in the next chapter, but carboxylic acids now are related to esters, and esters themselves have a whole bunch of different chemistry based on the fact that we have a leaving group attached. So we're starting to play this game where we can go in different directions depending upon what the job is to be done. We talk about secondary alcohols. They're a little bit different to primary alcohols because they only have one hydrogen attached. If you only have one attached, you can only take one off. And if you do that and you do the same type of reaction with this, this magic oxidant, which we'll develop in a second, you get a ketone. And the thing is that the ketone does not have an extra hydrogen. There's no hydrogen left on that carbonyl, so you can't replace it or remove it, and so that's done. And it's a nice chemical test to be able to tell what you have. If you isolate something from nature, you want to know if it's a primary alcohol or a secondary alcohol, oxidize it. If it's primary, it might go all the way to a carboxylic acid. If it's secondary, it'll stop at the ketone. And then be very careful with this one. If you have a tertiary alcohol, it will not react with an oxidant under normal conditions. Why is that? No hydrogen, simple as that. No H to remove or replace, and therefore it's not going to happen. So that's going to, again, differentiate that alcohol from the other different types. Now what we need to do today is talk about actual chemistry, talk about reagents. And I'm going to put an asterisk here, and I'm going to save this mechanism for later. Mainly because I don't want to get bogged down in 13, right? It's a very cumbersome mechanism, it's a very long mechanism, and it is easier to teach if you wait until later when we talk about carboxylic acid chemistry. So I'm going to come back to this later in terms of the mechanism, but you do need to know what happens, and I'll give you some explanation for why these things happen. What we're going to do is start out with sodium dichromate. Okay? You can use CrO3 and sulfuric acid, or you can use sodium dichromate, and they give you the same thing. When you mix these things up with sulfuric acid, this is the active species, chromium 6, and we'll call this chromic acid. And chromic acid is nasty stuff. It's very, very poisonous, but it's very powerful in terms of oxidizing. It's very good at oxidizing organic material. And we've got to remember each time we do this that every time you have an oxidation, you must have a reduction as well to go along with it. Something gets oxidized, something else gets reduced. And we need to keep a track of that. Well, if you produce this, chromium-6 is a very high oxidation state. And by that we mean electrons have been pulled away from the middle atom. If you think about +6, that's a very high oxidation state. The oxygens are pulling electrons away from the chromium. And so this chromium needs some electron density. It would rather be something like chromium-4 by picking up some electron density. So what it will do is form what we call a chromate ester. And the chemistry behind that is tricky, intricate. We'll save it for later, maybe even after the next exam. And we get the coupling of the chromium with the alcohol. And why is it an ester? Well, if we think about what an ester is for a carbon, there's a carbonyl, there's an oxygen, and there's a carbon attached. If you replace the chromium with a carbon, that's an ester. So you get better at this stuff by seeing the families, and you'll be able to say now, okay, that's a chromate ester. Later on we'll be able to say that's a sulfur ester, or that's a phosphorus ester, things like that, if you can see the similarities. So what I've got now is this chromate ester, and this is the key species that oxidizes and reduces. Now, the idea here is that the inorganic material, the chromium, is what drives the reaction. It really wants to get some electron density, and the organic material goes along with it, right, and ends up being oxidized. So what I've got here is an equivalent drawn out again, showing the hydrogen at the carbon with the OH, with the O group. And what's going to happen next is that we're going to get a reaction involving this as a base, picking off a hydrogen, and doing that. Now, what does that remind you of? What type of mechanism does that remind you of? E2, absolutely. It looks an awful lot like an E2. I'm going to put it in quotes. Some people think it's intramolecular, some people think it's intermolecular, but it looks an awful lot like an E2, which we're comfortable with. And you can think now, well, E2 often requires a base. And what type of bases do we use for E2s? Weak or strong? They're usually strong, aren't they? Now, that's an indication here of how potent this is, and how reactive this is, and how badly that chromium wants that electron density. This is a pretty weak base, right? Water's a very weak base. You don't need hydroxide here, you just need water. And in fact, this is happening at very high pH because very low pH, very strong acidity, because we're in sulfuric acid. So how badly does that chromium want to become chromium-4? That's how bad, right? You can use a very weak base like water to come in, take off the hydrogen, and lose this. Now, if you have to give me a term for that chromium, what's it behaving as? Looks like a leaving group, right? Looks like a leaving group, like bromium would take 2 electrons, something like that, or a tosylate would take 2 electrons. So it's taking 2 electrons, absorbing them in, and becoming reduced. So the oxidative reduction and the oxidation reduction chemistry is all happening in that structure. You should be okay with that because it is an E2 process if I were to ask you a question. Here is where the asterisk was. I'm going to get back to that later. You'll be much happier when we do that. There'll be a lot more explanation later on from a later chapter. Instead of jumping around chapters, let's just do that. Go ahead. Yes. I'll have a word with my typist. Okay, here's the gist of that. This is the summary of what I just said. In this chromate ester, it's set up now for the chromium to become reduced by picking up electron pairs, or an electron pair, I should say. And the whole point is that you can get chromium to have 2 electrons by doing an elimination process. This is just an acid-base reaction. This is forming the carbonyl right there. And that arrow, I think, is the key. That's where the chromium gets to pick up its 2 electrons and become reduced. And the outcome from that is to give you a carbonyl. So now we have a very powerful method to go from an alcohol, which we know are everywhere, ubiquitous, to aldehydes or to ketones, depending upon what we start with. So now we can start to use this in synthesis to be able to make different materials. Well, there's a problem with this set of reagents. This material here oxidizes whatever it wants. Okay? It's going to oxidize a primary alcohol and give you an aldehyde, but it isn't going to stop at the aldehyde. And that's a problem. And the main answer here, the main sort of gist of this, is the environment in which the reaction is run. Water. It's an aqueous type of reaction. The sulfuric acid comes in water, the dichromate dissolves up in water, and this is an aqueous environment. So what tends to happen is that the aldehyde, and again this is kind of later, but we can hopefully understand it, the aldehyde picks up a molecule of water. If it's in the presence of H2O, this is inevitable. We'll do a little bit more about this in the recitation, but that gives you this species. And in fact, if you have an aldehyde in an aqueous environment, it typically is this structure. It's called a hydrate. Okay? This molecule is called a hydrate. Obviously, you just picked up a molecule of water, became hydrated. Let's call it a hydrate. Now, for those of you who are getting into mechanism and starting to think, well, okay, I'm not going to cover the whole thing, but I can logically work out what might happen here. This OH and this OH are not a lot different to the starting OH. And sodium dichromate doesn't differentiate, and the chromic acid doesn't differentiate. So what you can get here is another molecule of the chromic acid forming a second chromate ester right there. And you get the same process over. In the starting reaction, you've got the primary alcohol forming a chromate ester, then it got reacted to give you the carbonyl. In this case, you get a second chromate ester, in which this simply gets attached here. Okay? And then you do the second elimination process, and that gives you another carbonyl. And if I've got another carbonyl here, with one OH attached, that happens to be a carboxylic acid. So that's useful if you want to go from here to here. So the last thing you need to make a note of on that slide is that if you oxidize a primary alcohol with chromic acid, which is either made from chromium trioxide and sulfuric acid, or it's made from sodium dichromate and sulfuric acid, you will go to the carboxylic acid. You will form this in the middle, but you won't stop there. Now, I'll say this, it might be a nonsense to some people, but it does need to be said. If you want to oxidize an aldehyde, you have access to an aldehyde, and you want to take it to a carboxylic acid, you can use the same reagent. You can use the dichromate, and you can use the chromic acid. If it does give you the aldehyde, and the aldehyde reaction is an intermediate product, then it should also react as a starter material, and that will give you a carboxylic acid. So we have a very powerful method now of going between the families, between alcohols and carboxylic acids. Mechanistically, most of it will come later. Well, it would be nice if we could stop at that aldehyde. Let me get rid of some noise here. It would be really useful if we can go from here to here, because we've already seen that aldehydes are very, very important structures for Grignard chemistry. If we can make an aldehyde, we can couple it with a Grignard and make a longer chain, and we can start to do some serious synthesis. Well, that was thought about, and people up in the Northeast, it was at Harvard, Corey and his group developed reagents like this. And this is very clever stuff. The mechanism will be very similar, but the environment now has changed. What's missing from this equation down here that was in that last experiment? Water, right? So no H2O. This is run under anhydrous conditions using methylene chloride as the solvent. Now, methylene chloride is an organic solvent, right? And all these things are quite polar. This is a salt, and this is a salt. So the idea here was, let's make this salt organic. There's an organic piece, right? You don't want to put sodium there, or else it might not dissolve up. And there's an organic piece right there. And so these things might well be soluble, and they are moderately soluble in the solvent, so they work. And the whole point was, if you don't have any water, you don't get any hydration. So if you do form an aldehyde, it stops there. It needs to form that hydrate to go further. If it doesn't form the hydrate, it'll stop. So what you've got here, again, mechanism a little bit later, is the use of something called pyridinium chlorochromate, which is abbreviated PCC. Okay? It would be nice if you knew the structures. And pyridinium dichromate, which are very, very closely related. They're still chromium-6. Both of these things are chromium-6. They react in the same way, except because there's no water available, you don't go further than the aldehyde. So this stops right here. That's the key. Now, I've seen already in office hours that some people are doing their homework at the end of the chapter there, and they're seeing this already. Hopefully this explains things a little bit. But you now have some very powerful chemistry. You can start with an alcohol and go wherever you want, really. You can go to the aldehyde or the carboxylic acid, or you can stop at the aldehyde. And obviously with an exam coming up in the next couple of weeks, you will have to do probably both. Fair enough? Now, if you start with a secondary alcohol, it just stops at the ketone. Ketones don't oxidize any further. So we have some very useful chemistry, which will be summarized on the last few slides here when we start to do synthesis. Pierce, you okay? Holman at the back, you okay? Right. Now, doing synthesis, you have to think, obviously. And can you close that door? Dr. Angelo? Thank you. You have to think. And most of the syntheses that I'll give you over the next semester will not be more than 10 steps. In the first part of the semester, it might not be more than 5 steps. Thank you. So for those of you who like elaborate, right, and on the final last year you put like 12 steps, that is an indication that maybe you're going in the wrong direction. And what we'll try to do now is be efficient and try to be sort of, we use the word elegant in synthesis. Try and keep it as efficient and simple and elegant as possible. And that comes by practice, and practice, and it all falls together. So what we'll try to do now is just think about the consequences of mixing some starter material with a reagent that we just developed and thinking about what needs to happen. And then think about it in a synthesis possibility where you've got to think about what to start with, what reagents to use to get to a given product. So the outcome here depends upon the identity of that material. What is it, primary or secondary? Primary. That's the first thing you do, is identify it as primary. Now we scribble. We're notorious for scribbling. I've got a couple of hydrogens right there. That is absolutely key to what happens next. If you have two hydrogens, you can oxidize all the way to a carboxylic acid. If you don't, you might go to a ketone. So in this case, the first reaction goes to the aldehyde. We usually don't stop there. In these conditions, which are aqueous, this will not be the isolated product. It just is too reactive and it goes further. So you get the second mechanistic step. This is not a separate reaction. You will go further. So overall, in the presence of the aqueous chromic acid dissolved up in water, you will go from the primary alcohol to the carboxylic acid. How would you stop at the aldehyde? Use the PCC or the PDC, right? And it's very easy to say those things, but we need to be careful with the chemistry. They're all chromium-6 reagents. They all do a similar type of mechanism, a similar type of process to get to the oxidized state, but it's the environment that changes. If you're in an aqueous environment, you go all the way to the carboxylic acid. If you're in something that's anhydrous, you can stop at the aldehyde. Does it matter for a ketone? If you take a secondary alcohol, do you need to use PCC, or can you use the other one as well? You can use the other one as well. You can use anything because they stop at the ketone. That's going to come with practice. Dominic? Carboxylic acid, not really. No. We will do one reaction later on where we break the bond and we get carbon dioxide, but that's a ways away. That's it. There's no more hydrogens there. You can't take them off. Okay? You will make carbon dioxide in one instance later, but that's a long way away. All right, so now we've got some useful reagents. We can start to do some chemistry. And this stuff, you know, I don't like to jump around in the book, and I don't like to sort of chop out too much because some of this is very interesting. I'll point this out now, and I'll do a little bit of a sales job for next year. I got to teach, or I'm teaching a new class this semester, which is the first new class I've taught in about 10 years. So this is kind of fun and exciting. And what tends to happen in the second semester of organic is that we spend all this time talking about functional groups and spectroscopy, and we get through most of the chapters. And then at the end of the chapters, we have these 3 chapters or 4 chapters, which is all application of this stuff in biology, in engineering, in polymers and stuff like that. And we never get enough time to cover it all. So what I suggested this past year was, why don't I run a class at the senior level, because we seem to be running out of options for people to take classes at the senior level in chemistry, where I can talk about this in more depth. So this is now a class that's running. If you know people in the senior chemistry classes, I have 24 people in there, which is great. And we're taking this into much greater depth. It's not biochemistry. It's looking at structures from an organic sense. It's all about mechanisms. So if you like mechanism, maybe you'll take this next year. It runs in the spring. And what we're talking about is how chemists will reduce a problem down to its minimum sort of requirements. Now, in biology, you have what we might call specificity. You have enzymes and systems that have been designed or have been evolved, whatever you want to call it, to do a certain job. You can imagine in biology you have all these chemicals floating around in solution, and how do things get done? It just seems crazy. It's all these things bubbling around in solution. But all of a sudden we seem to be able to metabolize these things or to use these things in a very sensible way to produce the materials we need to live. Well, one of the most sort of interesting things to me is this molecule. And it is a biological equivalent of this, NABH4. And this is FYI. If you want to know all about this, we'll do a little bit of it at the end of this term, and then we can do it in great detail if you take that class in the spring. It's a nice way if you're taking a PCAT, MCAT, GRE or anything to review organic and get some mechanistic ideas in review. Well, all right, I'm an organic chemist. I'm quite happy with that little thing down there, right? You've used this in lab, right, this week? Sodium borohydride. What was the solvent? Methanol was the solvent, right? So that adds up with the conditions we used in class. Well, this great structure here, very, very complicated, is a handle that is needed for the biological system to recognize it. An enzyme will pick this thing up and hold it in 3-dimensional space. Well, as an organic chemist, I look at that and I think, wow, that's really cool. There's lots of interesting things there. But I'm an organic chemist and I like to do synthesis. And I'm interested in the business part of the molecule. So all of this stuff, and this, you know, if you take biochemistry or you're a biologist, this is kind of sort of, you know, disheartening. Because all I do here as a chemist is do that. Because it doesn't change. And we had this nice discussion yesterday in the class because I've got people who've taken advanced level biochemistry, and I missed out one little letter, and that little letter in the name made a big difference in terms of the biology of the thing, but it made no difference whatsoever in terms of the chemistry of the thing, because it's a chemistry class. So this piece over here is the equivalent of sodium borohydride in biology. Now that tells you that this thing isn't so good in terms of specificity. It's going to reduce what it sees. Whereas these things have been evolved to be able to reduce certain things in certain instances. Very, very selective. Well, the chemistry here is kind of cool, because what happens is this forms a conjugated system, lots more to come on that, and it boots out H-. And so it does the same chemistry that we did with the borohydride, but more selectively. Now I'm just looking at this to show you that it's in the book and it's important, and we will talk about it later. But the chemistry here is kind of fun, because you can look at this as a chemist. It is a biological system, and as a chemist, you can look at the biological system and understand it. In this case, there is that molecule, NADH, nicotine adenine dinucleotide hydride, and there's the R group, okay? And what happens here is we push electrons in, and that hydrogen pushes towards the ketone, and then protonates, and we get an alcohol. It's exactly what we did with sodium borohydride. You've done that this week. So that's happening in systems, that's happening in you right now. But then you need to do the opposite too. Obviously in biology, you can't use dichromate. It'll kill you. Right? So you've got to use something a little bit more sensible. And it turns out that the opposite can happen. The oxidized component over there can now be used as an oxidant to react with alcohols to give you, in this case, a ketone. Right? So if you're thinking about where chemistry is and where biology is, obviously biology has a bit of a head start on us, right? But organic chemists are using biology as a sort of a template and as a example to try and develop reagents. So maybe in your lifetimes we'll get some chemistry where we can be much more selective and much more specific, and sodium borohydride isn't there just yet. So just keep an eye on that for later. But my point is partly, take my class next year, and also recognize that nature does, or we tend to mimic nature. So I'm going to go very quickly over this. Who has to take biochem? Show of hands. Who has to take biochem either here or later, at some stage in your lives? Who should be taking biochem? I'm looking at the engineers. Yes, you should, right? So biological engineering will be huge in the future. You'll learn all about this, the metabolism of carbon-based molecules, and a lot of it is based on oxidation reduction chemistry to produce things like energy and what have you. And a lot of it is simple organic chemistry. Taking an alcohol and then oxidizing it to the aldehyde state, and maybe oxidizing it further to the carboxylic acid. So what we're doing here in a synthetic sense is going to be huge in your futures if and when you take biochemistry. And that's it for that material now. I'm not going to spend any more time on that. What we will finish off in this chapter, because I will get this done today, I think, the homework is out there. I will put a recitation quiz up there in the next day or two, and I'll have that due by next Thursday maybe, give you a chance to get that done. And then we're into 14. Now, why don't alcohols oxidize? Because there's no hydrogen to take off. It's as simple as that. So when you look at a phenol, surely phenols should be the same. There's no hydrogen at that position to remove. But you can oxidize phenols. And this is important in technology to be able to make different types of antioxidants and stuff like that. And it also happens in biology. So we can start off with phenol itself. And what's the pKa here? 10. And we need this powerful oxidant, sodium dichromate, which will give you chromic acid, and you will make something called benzoquinone. Now, we don't know this yet, but that's kind of difficult to do. That system here, which we'll call a 6-pi system in the near future, is actually quite stable. And we'll do chemistry in which that reacts, but it comes back. The whole point of this system will be to get the benzene ring back. So that tells you that this isn't a trivial process. This isn't an easy process. If this is a pretty stable system, then it's quite difficult to get to there. That's why you need this type of reagent. So you can go from phenol to something like a benzoquinone. Now again, mechanistically, we're not quite there, but those of you who are starting to get this stuff, who might see yourselves doing this in the future, you should be able to sit down and scribble this out. You think about what we just did for the oxidation of an alcohol. This is the same type of thing. Reduction in this sense, I need to bring in H-. If I bring in H-, maybe I'm going to attack one of those things. That would give me something like this. After I protonate, maybe I'll get something like that. Okay? But then, how do I get to this system? Well, I can do this. I can have that proton seemingly move around. What process is that when a proton goes between a carbon and a carbonyl? Resonance is involved, but what was it called? We did it in alkyne chemistry where we took something that had a double bond and an OH and turned it into a ketone. Tautomerism. Yep, tautomerism. So that's just tautomerism, and that's a fairly simple mechanism that will enable you to get to there in the reduction sense. But what about the oxidation? What needs to come out of this molecule if I'm going to if I'm going to oxidize it? What do I need to get rid of? What's not in this product that is in this product? Hydrogens. I need to get rid of hydrogens. So mechanistically, for those of you who are keen on this stuff, maybe I make a chromate ester. Okay? Maybe I make a chromate ester. And then I need to get rid of some other hydrogen, and maybe my water comes in, because this has got to be in the aqueous environment here, and I do this. And then I start thinking about this, and then this, and then this, and then that. And there's the key event. Don't worry about that. Don't lose any sleep over that. You've got plenty of other things to lose sleep over. But that's where we're going, to be able to develop a mechanism based on the things that you already know. And I think at the end of the day there, you get 2 carbonyls. So again, you can oxidize these things if you use the powerful oxidizing reagents. There are systems out there, natural product systems used by all sorts of organisms as antioxidant type reagents, and you'll probably see a bit more of that later if you take classes at the senior level. So yeah, phenols are alcohols, they can be oxidized. Not quite as simple as the other systems, but they can be oxidized. This slide, just showing that it happens in nature, just put an asterisk on it and say later. We'll cover it later. It's more biochemistry than I care for at this point. So oxidation reduction is important. You now have methods to be able to do all sorts of different chemistry. And what I'm going to do for the last 20 minutes today to get ready for next week and 14 is to spend some time summarizing where we are. Because again, if you've been slow at this and you're not getting up to speed just yet, it's going to start getting overwhelming very quickly. Because we have covered a lot of things this term, which then add into a lot of things from last term, right? So we can now start to do synthesis. And at the end of each chapter now, we will have something called, synthesis strategies, how to think about using the chemistry we have developed to be able to make bigger molecules. The goal at the end of this is to get to about 34 steps on one of those homeworks so that you're confident with this stuff and you can use it on a test. Last semester, we spent an awful lot of time talking about alkanes. Very simple molecules, easy to get hold of from the ground. Good starter materials because we can develop sort of things like radical chemistry to put a halide on there, then you have a functional group to do something with, and then we could do this. Now, what type of chemistry is that? What type of reaction happens here with the bromine? Radicals, right? Initiation, propagation, termination, all that stuff to give that product. What chemistry happens there to be able to go from that alkane to that alkene? Elimination, and it would be an E2, right? It would be an E2 because it's under basic conditions. So then we had, an alkene. An alkene opened up an awful lot of different chemistry. The addition chemistry chapter was huge because now we have a weakly held pair of pi electrons that can be pushed elsewhere. We can do additions. We can do all sorts of ideas. What type of chemistry, thinking about what we've just done, what type of chemistry is that? What type of chemistry is happening there? It's a reduction. It's an addition of H2, which overall is a reduction. Now, that seems a bit redundant, but what's happening next in the near future is that. Do we all recognize that? Yes, I could do the real one, but you're going to make bigger molecules that are more expensive and you spent a lot of time doing the chemistry. And you do not want to lose that structure. So you've got to be very careful, and this will be quite testing in the near future. This is not going to be ethylene. This is not going to be ethane. It's going to be big molecule. And you've got to be careful when you do whatever you do, because you might do something to big molecule and that destroys what you're trying to achieve. So we're going to develop this in terms of selectivity and when to do what. With that in mind, once you have an alkene, from last semester you can go all sorts of places. We developed methods to go to alkynes. And alkynes became useful because we have a proton at the end which was moderately acidic. What was the pK approximately? 25. So it can be taken off with a powerful base and you can make a nucleophile which can then add to an alkyl halide and give you longer chains. So with that in mind, we can then think about, once we've done that, making alkenes. And yes, it's going around in circles. That's the whole point. So what we've got now are ways of making alkenes and alkynes and alkanes, and we can do all that sort of stuff. But the second semester opens up because we start to reduce and we start to oxidize. We now have much more in terms of flexibility. What we did so far in the last couple of days, the past couple of weeks, was start out either with alcohols or carbonyls. The limitation is often what's in your lab, what's available from the chemical companies in a cheap sense. The alcohol might be very expensive, the ketone might be very cheap, or the other way around. You obviously buy the less expensive one. Then you turn it into the other thing that you need. You can see here, if you want to oxidize something, you need an oxidant. You can then take out hydrogen, in this case make a ketone. And if you want to start with the ketone and you want to reduce it down to the alcohol, you need a reductant. Bit of advice with the weekend coming up. Next week, when we're into 14, and 14 to me is very straightforward and we do it very quickly, before we get to the spectroscopy, be happy with this stuff. Do not be getting 2 weeks from now thinking about this exam coming up and getting into this, because it just won't work. Yeah, you need to be doing it now. Well, this is kind of like Star Trek, isn't it? Right? Because then you boldly go where you boldly want to go, and that's just kind of, you split the infinitives. Go boldly, or boldly go. That's where it gets scary. That's where preparation is key. And again, looking at the stats, half of the people get through this term, 60 of you should get through, so that means you're going to put the effort in. We can also think about starting with different types of alcohols. This is the detail. Why do people use this class as an indication of success in pharmacy school or medical school or graduate school? Because it's difficult. And there's a lot of it, and it's thrown at you very quickly. And you have to absorb it and be able to use it to get through. We can start out with a secondary alcohol. We can make a ketone. We just did that. But we can start out with a primary alcohol, and now we have options. If you want to go to the carboxylic acid, you would choose to use dichromate. If you want to stop at the aldehyde, you choose one of the PCC or PDC reagents in a non-aqueous environment, knowing what those structures are, that they're chromium-6 and they will oxidize things, and you now have a nice method to stop at the aldehyde. Why are aldehydes useful? Because they react with Grignards. You can make alkyl chains. You can add things together to make more complex products. And again, this is just out there, out there in the universe. The chemical universe is very big. There are lots of different things you can do now. And this is just the beginning. So I would spend some time in the near future looking at simple interactions and simple relationships between the different families of molecules. You can think about alkynes as starter materials and look at their chemistry. We added things to them. We added water. We got carbonyls from alkynes. That involved a horrible mechanism, which was addition followed by tautomerism. But that there is to be used now as a method. We can see that alkynes can give us alkynes can give us alkenes. And you can go from alkenes to alcohols by doing addition. If you want to put the OH group on the more hindered or more substituted carbon, what do you use? If you want to, let's say you have an alkene like this, and you want to put the OH group there, what conditions do you use? Acid, H plus H2O. If you want to put the OH group on that carbon, which is the anti-Markovnikov outcome, what conditions do we need? What does that mean? Hydroboration, oxidation, absolutely. Those things need to be there, right? We're learning a language. You can't forget the stuff in the first term. But then we have the possibility of going here. And of course, from there, we can go back to there after we add things together. So it is starting to get kind of complicated because you have a whole semester and a couple of weeks of material on top of that. Well, I love this slide. I'm a big fan of this slide. I would like you to know this slide. This slide is your friend. Obviously, you're not going to see this slide on an exam. This has to be in your head. Somehow insert this slide into your hard drive in your head. And recognize that this is the toolkit. This is the functional group toolkit that we have developed over 17 weeks so far. There's a lot there. But for those of you who like problem solving, for those of you who like science or engineering, right, because they solve problems too, this is where it becomes enjoyable. Because now you get to put it into practice and you start to do problems and solve things. And if you can do this, it's a real kick, right? Because this is a difficult subject. If you can't do this, no good. So where do we want to start? I'm going to start over here. Alkynes are about the simplest thing we can get from crude oil. And they're not much fun because you can burn them, they can propel your car, but they don't do much chemistry. So you need to put something on there to be able to make them do chemistry. And one of the key features from last term was to be able to activate them as alkyl halides. That's key. You will find on my problem sets on that course pack thing, a lot of things start at alkanes. And the first thing you want to do with an alkane is is activated as a leaving group. Put a bromine on there. Or don't forget, tertiary better than secondary, better than primary, stuff like that. And you make alkyl halides. Alkyl halides are our friends because we can do all kinds of stuff with them. We can go to alkenes as we just did. And from alkenes we can go back to alkanes. And we can go back to alkyl halides. And the stuff we did last term, again, asking the same type of question. If I want to put a bromine on here, and I want to put an H on the other atom, what conditions do I use? It's a conspiracy. HBr. If I want to put a bromine on this carbon, and I want to put an H on here, what do I need? HBr and peroxides, which is summarized quite nicely, thank you very much, right there. Yeah, I would print this one out and keep it with you and practice these things. So then it gets complicated because all of a sudden we develop this semester some nice new methods to be able to do activation of alcohols as leaving groups by using SOCl2 or PBBr3. Nothing more complicated than SN2 chemistry, but new methods that have to be in there. And once we've got that, this is 3720. 3720 is all about getting here and then being able to do addition chemistry with nucleophiles such as Grignards, or from last semester we can use acetylides. We can do all sorts of chemistry now and being able to make more elaborate products. So that is key. I would say that needs to be looked at. So thinking about concepts, a lot of this will be on your own. For those of you who aren't in recitation, this is pretty much on your own. And most of you tend not to come to office hours who aren't in recitation, so you really are on your own. This can be tricky. The question might be, how do you turn this into this? The answer will be maybe several different ways. And this is where synthesis becomes competitive and it can be a lot of fun. You might have one group in Japan trying to make a very complex product and one group in the States, and they know they're both trying to make it and they want to get there first because then you'll be the famous group for making it. And they develop different chemistry. And maybe one group spends 100 steps and the other group took 150 steps. Which do you think is the better synthesis? Probably the 100 steps if they're efficient, right? So, you might get 20 steps in your reaction and somebody else might get 6. So the 6 is more elegant if the reactions are high yielding. And that just comes with practice. So here we'll see, again, relationships. Okay, alkynes are related to alkenes, related to alkanes. Alkenes are related to alcohols, which are related to carbonyls. You can also turn an alkyne into a carbonyl, if you're careful. You can turn alkanes into halides. We know that already. You can turn halides into alcohols, and you can turn alcohols into halides. When you write these things down, it becomes obvious. Well, we have different methods for doing this. And what we're starting to do now is a little bit of this, which we did last year. Thinking backwards, retrosynthesis. I will practice this in recitation. It's very, very simple once you get it, but it's confusing if you don't. The idea of, here's the target. What do I need to do to get to that target if I have a bottle of this? And by that I mean on the exam, you're given the constraints. You're given the starting materials that you have access to in your lab, and you've got to develop a synthesis. So in this case, I think I need to oxidize at some point, right? So what I might do, and the chemistry that we might do here, is simply add OH. That would give us this, and then oxidize. And that would give us the ketone. And my advice is, again, get on this now because you get lost. People will forget to oxidize. People will start attacking alcohols with Grignards. And alcohols react with Grignards through acid-base chemistry, not by addition chemistry, if it doesn't sink in. And you could do this. You could do last semester that, in which you went through the alkyne chemistry. That looks like a bit more difficult. If you had to think about that in terms of the lab, all right, this isn't particularly nice, but this is pretty nasty. Mercury is horrible. So maybe you want to avoid that. Maybe you would just choose to do that one. Fewer steps, as long as they're high yielding, maybe that's a better synthesis than we had previously. And that's why chemists, will never be unemployed because there are always new things to make and always new methods to develop. So some examples. 10 minutes just to finish off and get you set for the weekend. The weekend. Anything on this weekend? When's the Super Bowl? When? It's not this weekend, is it? It's the weekend after. Okay, I don't care anyway, so whatever. What's going on here is the expansion of carbon-carbon bond-forming chemistry from last term. Last term was all about alkynes. They were the sole source of nucleophilic carbon that we had at that point. Now we have a large number of possibilities. We can think about taking Grignards. And by now, you should be thinking about why that happens, how it happens, delta plus attacking delta negative, swapping a negative charge from a carbon to an oxygen, stabilizing the outcome. If you haven't had recitation on Monday, we'll do this on Monday and summarize everything. And after that, you get a quench step, and that gives you an alcohol. Now, can you oxidize that alcohol? If I treat that alcohol with PCC or PDC or sodium dichromate or chromic acid, will it oxidize? No, because it does not have a hydrogen right here. But I can start to use this in a very clever, very, very useful way. Course pack material, tons of practice on this. If you want to start with an aldehyde, which you might be able to make from an alcohol, what reagent would you need to take that alcohol to that aldehyde? PCC or PDC in dichloromethane. And you isolate the aldehyde, and you make sure it's the right stuff. And then you bring this in, and you make a longer chain. And that's a methyl group, but you can bring in whatever you want. You know, you can bring in all sorts of different stuff at the end of that chain, as long as it's got a bromine at the end. And then you can start to make very elaborate products. Now, that's not the end of that, because I can take this hydrogen out. If I take that hydrogen out, what type of product will I get? Ketone. And ketones added with Grignards. So I can go again. And I can make very elaborate products by doing the same type of chemistry again. One of the limitations of this Grignard stuff was when you reacted with an ester, because the two equivalents come in, and they both have to be the same. You can't mix and match this. So if you want to make an alcohol, a tertiary alcohol that has two of the same groups attached, bring in maybe an ester, bring in a Grignard. Now, question again, can I oxidize this thing? No. Next week, when we do chapter 14, I'll be able to use that quite nicely. I'll be able to make alkenes, I'll be able to make tosylates, bromides, I'll be able to do ether chemistry that we'll deal with in 14. But so far, we're doing carbon-carbon bond forming reactions. So here, I think, is an important point. We can start with the primary alcohol, which are everywhere. You know, you go in that organic lab that you're working in, there's a bottle of propanol in there somewhere. Every lab has it, right? It's like salt, you know, it's like in a kitchen, you need salt. It's one of those things that has to be in there. And you can go from here to here, and I'm leading to the problems on the website. What chemistry do you need to do to get from that primary alcohol to that aldehyde? You need to oxidize it. Do I use dichromate? Do I use CR6? Do I use water? What do I need to use? I want to stop at the aldehyde. PCC in a non-aqueous solvent. And that gives me the aldehyde. So then I can add some sort of Grignard species, RMGX. And we know delta negative will go after the carbonyl, and you are knitting together two pieces. That gives you a more elaborate alcohol. It happens to be a secondary alcohol, and we've tried over the past week to hammer home the idea that secondary alcohols are related to ketones. So you can go to that ketone quite easily now. What reagents would you use here? Any ideas? PCC would work, or dichromate would work. Any of them would work, because you can't over-oxidize that ketone. So all of a sudden we've gone there. And let's say I wanted to go further. If I brought in a second Grignard, I can now make a more elaborate structure, and this could be anything. You can now make a much bigger molecule by simply clicking the things together, by doing simple sort of Lego assembly, putting the blocks together to make different products. So now we've got multiple step syntheses. Your problem is that you'll be asked to design this and go back. Asked to come up with the steps, asked to come up with the reagents to make sure that this thing works efficiently. Right, last few words, and then we'll break. We did some of this last term, and you need to bring it with you. And the question before was, is it better to do one way or the other? And the answer is yes. Or no, or yes, depending upon the situation. Sometimes on paper, everything works great. Sometimes in the lab, it doesn't work. You can have a 10-step synthesis using older chemistry that is just as good as a 4-step synthesis here, but now, economy, time, effort, maybe the 4-step synthesis is where you want to be. Last semester, if you wanted to make this molecule, which is the gist of this slide, we would have done it using this alkyne chemistry. We have a shorter chain here, we would count how many carbons, we bring in that extra carbon to make the chain the right length, and we would get here by hydration. Now, efficiency is the key. See if you get this, it's a big good place to leave. If I hydrate that system by the chemistry we used last term, by bringing in H plus and H2O, do I just get one product? No, why not? You'll get maybe a 50-50 mixture of that and maybe the one with the carbonyl is there. Yeah? And the one you want is this one. You have to distill the other one away. You lose half your material. So maybe that's not so efficient. So maybe we have a better method now. Maybe we can start with this aldehyde, which can come from an alcohol easy enough. We can do the Grignard chemistry and make that, and you put the alcohol exactly where you want it to be, and then you oxidize and you get to there. I'd argue that synthesis is much better than the one above it, because you don't waste half your material. And if this is on big scale, you know, a reaction flask as big as this building, that's expensive. So those features are important. So last couple of bits and pieces here. Getting you ready for synthesis, getting you ready to, you know, I'm telling you now that having done oxidation reduction chemistry, you have access to all kinds of different materials by doing these types of reactions. In this example, we could do older chemistry from last semester. We could turn this into the carbonyl by the hydroboration oxidation, where the O goes on the end of the molecule. Then we can do a Grignard reaction, and then we can oxidize, right? And that then could be 5 steps. I would suggest maybe 10 steps will be the max that we'll expect in terms of a synthesis in the next couple of weeks, couple of months. So that's the end of that. Give you a second. 13 is a big chapter. 14 is not. But 14 goes very quickly. I'll guarantee I'll be done with 14 by next Friday. 15 is completely different. It's spectroscopy. I'm trying to keep up with the lab so that you're looking at the stuff in lecture at the same time you're doing it in lab. Get onto this stuff, do the homework as soon as you can, and do not get behind. All right, see you next week.